Alright, just a quick example on how you find the zeros of a polynomial function. Now there are essentially 3 steps in doing this. The first one, we are going to try to find all the possible rational zeros. Now rational numbers are just numbers that could be written as fractions, so that could be a fraction, an integer, a positive or negative whole number, essentially 0. Can't be things that are irrational like square roots and things like pi. Those are irrational numbers. So the rational numbers we have are always of the form p and q, where p is going to be the factors of the last number and q is going to be factors of the first number. So p in our case is 5 or negative 5. So the factors of negative 5 or 5 are plus minus 5 and plus minus 1. Because 5 times negative 1 or negative 5 times positive 1 is 5. Now q is really easy in this one because it's just a 1 in front here, so q is 1. So my first step to find the possible zeros are going to be to take all of these numbers, 5, plus or minus 5, plus or minus 1, and divide them by all these numbers, which is just 1. So that's going to give me possible rational zeros of plus minus 1 and plus minus 5. There could be lots and lots and lots more of these. In this case, there's only 4. Now these all won't be zeros. And again, a zero, remember, a zero is when I plug it in and get 0. Because whatever your highest exponent is, that's how many zeros we're going to have. So in this problem, we're only going to have 3 zeros. And there are 4 numbers here. There's 5, negative 5, 1, and negative 1. So our second step is going to be to determine which of these are rational zeros. So which of these would I plug in and would it give me 0? So I can plug all 4 of these numbers into the function and see which ones give me 0. But that's kind of a lot of work as well. So a lot of times what we'll do is we will use the graph. Because the theory says the function is 0 when it crosses the x-axis as well. So this graph, if I sketch it, looks something like this. On your worksheet of the day, it actually will give you a little graph so you can see where it crosses. So this graph only crosses one place, and that place is at 1. So one of my zeros is 1. So what I'm going to claim to you is if I put in 1 to my function, which would be 1 cubed minus 1 squared plus 5 times 1 minus 5, I would get 0. Because it crosses the graph at a y of 0, so plugging in 1 would give us 0. If I plug in the 5, the negative 5, or the negative 1, I get something else. So our final step are to find irrational, and complex things with the I, roots. Now what we're going to do is we have some roots here. In this case, we have 1 root. So once we have that 1 root, or 2 roots, or whatever it was, we'll do this example with 1, then we'll do another one with 2. The first thing we will do is we will do the synthetic division on those roots. So I will take that 1 and I will synthetically divide my polynomial. So 1, negative 1, 5, negative 5. And I'm just getting those constants from this polynomial. It's just the numbers in front of each term. So I'll bring down the 1, and then I'll do 1 times 1, which is 1. Negative 1 plus 1 is 0. 1 times 0 is 5. Or 1 times 0 is 0. 5 plus 0 is 5. And then 1 times 5 is 0. I like to put a little box around here because this is my remainder, and my remainder should be 0. Because if you have a 0, when you divide it out, it should give you a remainder of 0. Now, because this was a 3rd degree and I divided out twice, this is going to leave me with a quadratic. X squared plus 5, and I simply set that equal to 0 to find my other 2 roots. So in this case, this is a pretty little easy equation to solve. we're just solving x squared plus 5 equals 0. So I'll subtract 5 from both sides, so I'll get x squared equals negative 5. And then I could take the square root of both sides, which will give me x equal plus or minus the square root of negative 5. And the square root of a negative number always gives me the imaginary unit. So that negative square root just comes out, and you can just put an I out front, and it just becomes I square root of 5. So our other two roots are positive I square root of 5 and negative I square root of 5. So this one has one rational real root and two complex roots. Doesn't have to be that. They could all be real. Those could be irrational. If this was, say, a minus 5, I'd add it and it would just be square root of 5, and that's fine too. All right, let's look at one more. So this one, I'm going to try to find all the zeros of f of x equal x to the fourth minus 2x squared minus 11x minus 30. Okay, because this thing has degree 4, remember this thing is going to have 4 zeros. So there are 4 numbers that I can plug into this function and get 0. Now I'm going to do the same process I did before. I'm going to look for the possible rational roots or rational zeros in that form p over q. Now p in this case is 30, so there's lots more factors, lots more things multiplied to 30. 1 and 30, 2 and 15, 3 and 10, 5 and 6. I think that's everything that multiplies to 30. And then for the number in front again, it's just 1. So when I'm making my list, I'm going to take all of these, and you got to be careful when you're taking ALEKS quizzes and sometimes it'll say just possible roots. And if it just wants the possible, it just wants you to make this list. And if it says find the roots, it wants you to do, or find the zeros, it wants you to do all this other work. So if I do all the p's over all the q's just 1, so it's just my list of p's. So it's plus minus 1, plus minus 30, 2, 15, 3 and 10, 5 and 6. So this is quite a long list. So if this would not be very efficient to plug in to my graph or to my function, to plug all these different numbers in and see which ones gave me 0. So again, I'm going to look at the graph, and my graph looks something like this. I'm just kind of sketching it on the calculator. It looks something like that. So it crosses at -2 and at 3. The most times it would have crossed is 4 times, because we have 4 zeros possible. So the most it would have been is 4. It's only 2 in this case. So that's good. So I know 2 of my values. I know -2 and I know 3. So my actual rational zeros are -2 and 3. So that means if I were to plug in -2 or I would plug in 3, I would get 0 for both. So you can do that, you can check it. I don't think it's a terrible idea to plug it in. Now the key thing in here is we're still missing 2 zeros and we have 2 roots. In the previous problem, we only found 1 root with our graph, and we divided out, and we found the last 2. In this case, we're going to have to divide out twice. And this is what kind of throws people sometimes. So I'm going to do the same thing I did before. I'm going to pick one of the zeros. It doesn't matter which one. I'm just picking -2 first for fun. So I have -2, and I'm going to take my numbers from my polynomial, which are 1 and 0. Notice the second number is 0 because there is no x cubed term. It starts with 4. There's no cube, so I put a 0. -2, -11, and -30. Now I'll do the synthetic division, and hopefully I will get a remainder of 0. If I don't have a remainder of 0, then my graph is wrong. Something is wrong. So I get 1, -2, -2, 4. -2 and 4 is 2. -2 times 2 is -4. Negative 11 plus negative 4 is negative 15. Negative 2 times negative 15 is 30. And there is my remainder of 0. Now, what a lot of people will do now with a 3, they'll go back to the beginning and divide 3 out again. And that doesn't really get us anywhere. So here is the trick. This is what you have to make sure you do. Now, I'm going to basically ignore this remainder, and I'm just going to look at these 4 numbers. And now from these 4 numbers, I'm going to go from the same process, but instead of the 2, I'm going to use the 3. So I'm going to drop the 1. 3 times 1 is 3. Negative 2 and 3 is 1. 3 times 1 is 3. 2 plus 3 is 5. And then 3 times 5 is 15. And there is another remainder of 0. So the whole key thing is when you get to this end thing, if you divided out everything you can, you should get a quadratic. And we do. This is going to be 1x squared plus 1x plus 5. And so that's how we're going to find our other 2 zeros. We're going to take that remaining quadratic and set it equal to 0. Now this is not as easy as the last one where you could just move something to the other side and just solve for x. Here we'll have to use like a quadratic formula or something. So I'm going to do quadratic formula to find my other 2 zeros. So this is going to be x equals negative 1 plus or minus square root. 1 squared is 1. Minus 4 times 1 times 5 all over 2 times 1. So that is going to give me x equals negative 1 plus or minus the square root of negative 19, because you got 1 minus 20 over 2. And so just to clean it up a little bit, I can write this as negative 1 plus or minus I radical 19 over 2. And again, because it's got the plus minus, that's why my other 2 zeros are there. So my last 2 zeros, they're going to be kind of hard to squeeze in here, so I'll kind of write them down here. So my last 2 zeros are going to be negative 1 plus I radical 19 over 2. And then this guy, my last 0, is going to be negative 1 minus I radical 19 over 2. So I have 1, 2, 3, 4 zeros for this problem. Now, it's quite a process. You have to find the rational zeros, then you have to figure out which ones of those work by plugging in, or more favorably, graphing it and see which ones cross, dividing those out, and then getting to a quadratic. And you should always get to a quadratic, especially in this class. So if you don't, probably look for more zeros or something of that ilk. So just a couple quick questions. These are ones that are pretty common to see on ALEKS quizzes and tests, and obviously on this worksheet of the day that we're going to be doing for today. So just wanted to give you a quick example, but if you do have more questions, I please encourage you to reach out to me.